Welcome to Maths with EJD. Still talking about numerical analysis. We are now focused on interpolations and approximations. And in this particular video, our focus will be on spline functions and cubic splines, which have come to be very useful when we talk about interpolation. So let's start off with the idea of spline functions. Hmm. Spline functions are piecewise. They are piecewise polynomial functions used to approximate or interpolate data points or interpolate data points smoothly. No, the whole idea of interpolation is that probably you have a few data points, and then you now want to create an expression that can help you, using those few data points, you now want to get other data points. So that's basically what the idea of interpolation is about. Okay. So spline functions are piecewise polynomial functions used to approximate or interpolate data points smoothly. They are primarily, they are primarily used in numerical analysis. Of course, that's what we are considering. In numerical analysis, computer graphics, computer graphics, and data fitting, and data fitting due to their due to their flexibility, flexibility in handling complex curves, in handling complex curves. Okay. The most common type, the most common type of spline functions, most common type of spline functions are piecewise polynomials, piecewise polynomials that join at certain points. Piecewise polynomials that join at certain points, known as knots, known as knots to maintain smoothness, to maintain smoothness. Okay. A basic type, a basic type of spline is the lead. A basic type of spline is the linear spline. Is the linear spline where the function, where the function is piecewise linear. The function is piecewise linear. That means that between one point and the other, it's just you have just straight lines. It's piecewise linear between points, between knots. It's piecewise linear between the knots. Okay. However, being linear to it is going to be very sharp. So, however, for smoother curves, we often, however, for smoother curves, we often use higher degree polynomials. And one popular example example is the cubic spline, which is our focus in this video, is the cubic spline. Okay, so now that we have made mention of cubic splines, let's see what they are about. Cubic splines. So cubic splines are a type of spline. They are a type of spline where each piece of the spline, each piece of the spline function, each piece of the spline function is a cubic polynomial. The cubic polynomial. The cubic polynomial, that is a polynomial of degree 3, polynomial of degree 3 that fits the data points, between the knots, The advantage of cubic splines over simpler linear splines is that they ensure smoothness not only in the functions value, but also in its first and second derivatives. This leads to a much smoother and more natural approximation of curves, I mean, to drive the point home, right? Imagine that um, you have imagine that you have something like this, and this is your x, this is the origin, and this is f of x or y, right? So and the whole idea of interpolation is that you have different points. Maybe you have a point here, you have another one here, you have another one here, and then you have one here. So if you are going to be using linear splines, that means you're just going to join this to this with direct lines, and that will just be, and that's what you end up getting. That's the whole idea of spline, is that from between, so these black dots now, these points now, they are like actually what you call the knots. But in the case of cubic spline, we are then going to have maybe something much smoother that just goes, it flows more freely, like it just goes. Okay, that's not even looking as good as I would like it to be. Let me make one more attempt and see how that works. Okay, so it's more like you're just going to be, okay, uh, I have an idea. Let me use this. Let me use a marker. So, it just goes smoothly like that. Smoothly. So if you use a cubic spline, it's smoother than when you have a linear spline, which just use straight lines to join things up. Now, at the end of this, towards the end of the video, I'm going to show you a Python implementation of cubic spline so you understand what this is about. But for now, let's keep going in this. So now let's talk about characteristics of cubic spline, since that's our focus. Characteristics of cubic splines. So the smoothness is such a big deal, right? Characteristics of cubic splines. First of all, The spline function, the spline function is defined piecewise, What the piecewise thing is what I just told you that whatever you have is between the points, like between this point and this point, you have a cubic expression. Between this point and this one, you have another cubic expression. You have between this point and another one, you have another cubic expression. So everything just smoothens out over time. Instead of having one expression that joins all the lines together. Okay. So the spline function is defined piecewise as cubic polynomials, between each pair, between each pair of consecutive data points, just like what I showed up there, consecutive data points, which can be called knots. So each data point is called a knot. Then we go to the next idea, that the first and second derivatives. So the advantage of a cubic polynomial is that you can get a cubic spline is that you can get its first and second derivatives. The first and second derivatives of the spline are continuous at the knots. They are continuous at the knots. And that's an unusual thing, right? But it's ensured. That's the essence of a spline. So they are continuous at the knots, ensuring smoothness. Otherwise, those knots will actually be points of discontinuities where, the graph jumps or something like that, or it has a sharp restart, or so to speak. So the spline is typically chosen the spline is typically chosen to satisfy boundary conditions. Okay, to satisfy boundary conditions such as fixing the slope or curvature, at the endpoints. That's talking about natural cubic splines. Okay, having said all this, can we consider the mathematical formulation of these splines? Mathematical formulation. Okay, let me maintain the same kind of pen tip for this. Okay, mathematical formulation. Okay, so imagine that let the data points be, say, x1, y1, x2, y2, and that goes on until you get to xn, yn. Okay, so we wish to find a cubic spline sx that interpolates, these points. Okay, so each piece of the spline between xi and xi plus 1 is given by a cubic polynomial. So that means that between x1 and x2, between x1 and x2, you have a cubic polynomial. Between x2 and x3, you have a cubic polynomial. Between x3 and x4, you have a cubic polynomial, and so on and so forth. So you have a polynomial defined for each interval, So for each one step like that, that's what the cubic polynomial is defined for, instead of the whole point at once, which we have the possibility of doing if you're doing like a cubic fitting right? So that's why cubic spline is more accurate than just cubic fitting like that. So an x is given by a cubic polynomial. So and that cubic polynomial looks something like this. You have Si of x equals AI into x minus xi cube, okay, plus bi into x minus xi squared plus ci into x minus xi, okay, then all of that now plus di, okay, and this is happening for x belonging to the interval xi plus 1. Okay, so this whole expression now is what you have between x1 and x2, for instance, or x2 and x3 and everything. So it means that if you are talking about the first spline, that means the first interval, so you're going to have s1 equals a1 into x minus x1 cube plus b1, okay, plus this is bi now, right? But if I is 1, so you have b1 into x minus x1 squared plus c1 x into x1 plus d1. That's for x1 to x2, like that. So at the end of the day, the goal is to find the coefficients. The goal is to find the coefficients. So we are looking for the coefficients AI, BI, CI, and DI for each polynomial. For each polynomial. That's what we are looking for. Okay. So if we move on, from here, then we'll be talking about some boundary conditions because, since we are talking about piecewise jump between one point and the other, so we need to also pay attention to boundary conditions because we want to maintain overall smoothness, though the cubic splines are between one knot and the other. So here now, to ensure the spline is well behaved, okay, we need to set boundary conditions. Okay. For example, the natural cubic spline, which I've mentioned before, I believe, the natural cubic spline assumes that the second derivative at the endpoints is 0. That is, you have this, that s prime prime of x1 is equal to 0 and s prime prime of xn is equal to 0. That's one boundary that helps. Then the fact that s prime of x1 is equal to slope, the first slope, and s prime of xn is actually the end slope, like that. So the natural cubic spline assumes that the second derivative at the endpoints is actually 0, So with all of this stated, then let's talk about let's take an example and see how it goes. So consider the following data points. 1, 2, 2, 3, 3, 5, 3, 5, and 4, 4. Okay. And we want to construct a natural cubic spline, cubic spline that passes through these points, that passes through these points. Okay. So the first step, imagine step one, we have to set up the system of equations. So we need to set up the system of equations for the cubic splines. For the cubic splines. So first, for the interval x1, x2, which is 1, 2. As you can see from here for the interval, so this interval 1 to 2 now, that's x1. So this is x1, this is x2. So for that interval, so we have, so if you follow the formula up here, all the S and everything, so all these formulas up here, this formula now, so we have S1x, A1 into x minus 1 cube plus B3, blah, blah, blah. So that's what that is about. So, and of course, we already know all the x1. So, this is from the equation, from the question, right? This is x1, this is x2, this is x3, and this is x4, like that. So we know our focus now is on x1. So we are going to have S1x into A1, x minus x1 is 1, so x minus 1 cube plus B1, x minus 1 squared plus C1, x minus 1 plus D1. So we are going to look for A1, B1, C1, and D1. So we basically have C1, S1 of x to be A1 into x minus 1 cube plus B1 into x minus 1 squared into C1, Cx minus 1 plus D1. Okay, so we are looking for all, so that is the first expression that we have. So in setting up the equation, so next we go for the second interval. So for the interval x2 comma x3, which is 2 comma 3, like this. So we have, see x2 x3 up there, that's actually this x2 x3, so that's 2 3, right? So we have that expression again. So our x2 now is 2, so it means we are going to have s2 of x equals a2 into x minus 2 cube plus b2 into x minus 2 squared plus c2 into x minus 2 plus d2. So we have another expression for that next interval. So then and the next interval, and the interval after that is 3, 4. Interestingly, that's the last interval we have. So we now have from 3 to 4 now. So that's x3, x4. So the more data points we have, the more. So for instance, here now we have 4 data points. So it means we are going to have 3 equations to set up. If we have 10 intervals, we are going to have 10 data points. We're going to have 9 equations to set up. Okay. So now we say for the interval x3, x4, which is 3 comma 4, we now have so our x3 is 3, so we just have S3. It's not 3 because we are talking about the third point. No, because x3 is actually 3. X3 could have been anything else, not 3. Just like x2 could have may not have been 2. But interestingly, x1, x2, x3 here, 1, 2, 3. But it doesn't always have to be like that. It's just because that's the data point we have. So x1, x2, x3 could be 10, 9, 4, 5, 15, 22, anything. So S3x will now be A3 into x minus 3 cube plus b3 into x minus 3 squared plus c3 into x minus 3 plus d3. So with that done, so that's now the last equation for the cubic spline that we need. Okay. So once that is settled, then we could then go ahead and talk about, say, step 3. So step 3 now is to apply the continuity conditions. Apply the continuity conditions. Okay. Apply the continuity conditions. So first of all, we have the function continuity. Function continuity. So for the function continuity, we say that the spline must pass through each data point, because we want smoothness. The spline must pass through each data point. So that means that S1 of 1 must be equal to 2, because, each data point. So S1 of 1 must be equal to 2, just like S2 of 2 must be equal to 3, and S2 of and S3 of 3 and S3 of 3 must be equal to 5. Just like okay, let me see. S1 of 1 must be equal to 2, and S1 of 2 must be equal to 3. At the same time, S2 of 3. Okay. Let's be careful here. So S1 of 1 must be equal to 2, then S1 of 2 must be equal to 3. So those two, right? S1 of 1 is equal to 2, S1 of 2 is equal to 3. Then S2, S1 is joining points 1 and 2. So that's why those 2 points must be reflected. So that S1 of 1 is 2 and S1 of 2 is 3. Then apart from that, we should also have that S2 of 2 is 3 and S2 of 3 is equal to 5. So that's to ensure, we have something like these two now. They are this. So S1 of 2 is the same thing as S2 of 2. So it's that same point to ensure we have that continuity that we're talking about. Then we now go further to say that S3 of 3 should be equal to 5. So that means this and this are the same. Then finally, S3 of 4 is now equal to 4. So, you can see we make sure that all the points are just everything just keeps going. And that's for the function continuity. So we have another type of continuity, which is about the first derivative. We have the first derivative continuity, first derivative continuity. So for first derivative continuity, what we need here is that the first derivatives of the spline functions, the first derivatives of the spline functions must be equal at the knots. So what that simply means is that S1 prime of 2 should be equal to S2 prime of 2. Then S2 prime of 3 must be equal to S3 prime of 3. So that ensures that we have a smooth curve going on. That's talking about first derivative continuity. And then the last type of continuity we have is the second derivative continuity. Since we're talking about a cubic spline now, so we can have the function, the first derivative, and the second derivative. So second derivative continuity is now, so it's such that the second derivatives of the spline functions of the spline functions must be equal at the knots. Okay. So what that simply means is that S1 prime prime of 2 is equal to S2 prime prime of 2. And again, S2 prime prime of 3 is equal to S3 prime prime of 3. So the second derivatives of the spline functions must be equal at the knots. So having taken care of that, then we can go back and we can go again and look at say step 3. So step 3 in this case, we have to apply the boundary conditions. Apply the boundary conditions. Apply the boundary conditions. So I think we stated some of the boundary conditions previously. So for a natural cubic spline, the second derivatives, the second derivatives are the endpoints. Are 0. Second derivative are 0. So we have that S1 prime prime of 1 is equal to 0, just like S3 prime prime, of 4 is also equal to 0. So for a natural cubic spline, right, the second derivatives are the endpoints are 0. So S1 prime prime is 0 and S4 prime prime is equal to 0 because, that's the starting point and the termination points. So that's step 3 now. Now let's talk about step 4. Imagine that, let's go for step 4 now. So step 4, step 4. So at step 4, we solve the system of equations. So we have set up all the equations. So we just solve the system of equations. It's a tedious thing, so I won't bother. I will just, so after all this explanation, we'll just implement with Python to see the beauty of all the stories we've been telling. So, basically now, we want to solve the systems to get all the coefficients we had up there. So by solving the system of equations, formed by the continuity and boundary conditions, by the continuity and boundary conditions, boundary conditions. Okay. We can obtain the coefficients. A1, AI, BI, CI, DI for each piece of the cubic spline, Okay. So what happens is that we get, so what does the final result look like? Okay. So the final result, of course, after this, I'm going to show the Python code, which we'll understand all these things better. So the solution gives us the cubic polynomials. So we actually have the cubic polynomials starting from a knot and terminating at the next one. The solution gives us the cubic polynomials for each interval, that interpolates the points smoothly, satisfying both the function, and derivative continuity as well as the boundary conditions, the boundary conditions. Okay, so it's a very tedious process for sure. So in conclusion, cubic splines are a powerful tool for interpolation, especially when smoothness and continuity are required. The method ensures that the resulting curve is not only continuous but also smooth in both its first and second derivatives, making it ideal for applications in data fitting, computer graphics, and numerical modeling. All right, so let's go ahead and see the Python implementation of this. So look at this now. Um, these are the points we are interpolating: 1, 2, 2, 3, 3, 5, 4, 4. Just like we had before. Is that it? 1, 2, 2, 3, 3, 5, 4, 4. Yes. I think that's it, right? That's looking a bit different. Is that? Yeah, it's 4, 4. Yes. So 1, 2, 2, 3, 3, 5, 4, 4, like that. So we create the cubic spline using the data points. So that's in line 10. So we say spline, cubic spline, X, Y, B, C type natural, because we're talking about natural cubic spline. So we divide. So since we have 4 data points now, so we are moving from 1 to 4 using 500 divisions to make it very fine. So this 500 is just the number of divisions into which you are separating uh, the beginning and the end, 1 to 4. Then Y actually gives us the spline for X that we have declared. So we then plot the spline in figure 17, I mean in line 17 and 18. So this is all setting the size and the color and things like that. Then we plot the original data points. So the original data points will be in red, right? These are the points 1, 2, 2, 3, 3, 5, and 4, 4. Then the output, we have the cubic spline expressions for each interval. So for each interval now we have the cubic spline equations. So you see for I in range length x minus 1, that's for 1 to 2 we get the equation just like you saw there. That's all those SIX equations, right? For 2 to 3 we have another one. For 3 to 4 we have another one. So 3 of those equations in all. So because at the end of the day we are just looking for AI, BI, CI, and DI, and those are the things you're looking for. So you're going to see all of that too. And then so this is how the expression is, the general equation, right? And then if you go ahead and just run it, you see something very smooth and beautiful. So you see that now. So you see S1 of X, that's between interval between 1 and 2. That's the first equation there is what you have. That's 0.467 x minus 1 cube minus, that's minus 0.000, like to three significant figures. It's really small. Let me see if I can increase the significant figures. Okay, it's 3 right now. Let me make it 6 and see what it looks like. Let me say that 6. Or let me make it 5, okay? So we can see, even for 5, we can still see okay, that's just for the first one, right? Let's make it this one 5, 2. And also this one, let's make it 5. Okay. And then this one also is 5. So probably we can see, oh, even to 5, it is still 0. So that means it's a very tiny number. So you can see we have 5 zeros now. So we can still see, for that first one, we can still see the number. So this is the cubic expression that fits this interval 1 to 2, that blue interval. Then for the orange interval, it is S2 of X that fits it. So that means this is A1, uh, B1. A1 is 0.467, B1 is 0.00 something, C1 is this, and D1 is 2. Then for S2 now, we have A2 is, so S2 is the equation that fits this orange part, it is the one that fits this orange part. So that means A2 is minus 4 over 3. That's minus 1.3333. Then B2 is actually 1.4. Then C2 is 1.9 over 3. Then D2 is 3. Then S3 is the cubic expression that fits the last part, now that green part. So that means that A3 is 0.867, then B3 is minus 2.6, C3 is 0.733, and D3 is 5. So so if you are going to do that manually, it would have been so tedious. And then you see this fitting coming on this sweetly. So polynomial 1, that's S1 of X, polynomial 3, polynomial 2, the orange, that's S2 of X, and polynomial 3, the green, that is S3 of X. Then the original point we're interpolating is this, this is 1, 2, this is 2, 3, this is 3, 5, and then this is 4, 4. So you can see everything just goes smoothly like that. So we use the cubic expression to join the points together, and then the whole thing now looks like just one thing. So, and that is the beauty of cubic splines. So if I add one more point, for instance, if I add one more point, let's see what happens. So let's say I add 5, comma 7. Okay, 5, 7. Let's see what that brings. Okay, so you see, wow, this is cool. So this is yet another thing because I've added another I've added 5, 7 now. What if, I mean, you can keep adding stuff like that, just like the previous ones too. That's why the Python code aspect of things is very nice. So if you keep adding things, you keep getting it keeps going like that. So the code, but if you had to do it manually, it can be pretty tedious. So let's say I have 8 comma, say 8 comma 10, 8 comma 10. We have this. So it keeps going like that. So we have for each interval. So you see new intervals are joining up, and then we keep having this uh beautiful thing. Okay. So that's how that goes. That's how that goes. So let me return it to what we have. So if you're going to have access to the Python code, if you follow me on Facebook, you can copy the code on my timeline and then just play with it, extend it, and see how it all goes. I'm not able to put it on YouTube because this code involves some corner brackets which are not allowed on YouTube. I wonder why that is. But I mean, if you can follow on Facebook, I'll put the code right there for you. And that is B Spline. The beauty of cubic B Spline is that you have that smoothness going. If you have subscribed to this channel, thank you very much for that. And if you haven't, please go ahead and do that because there's a lot more to learn. I'm still going to be talking about least square approximation for line fitting and for solving over what is that thing called now? Over determined equations. That's the equation where you have more variables than equations. Normally for you to get proper answers, you need your number of equations should be equal to the number of variables. But when you have higher number of variables, I mean you have more variables, more equations than variables, or something like that. So you are going to see that. And then we're still going to see Chebyshev polynomial interpolation. So all of these are still waiting. So subscribe, hit the notification bell so you can always get alerted anytime a new video is released. Then comment. Let me know how helpful these videos are. And let me know if there's a topic you'd like me to teach or a problem you'd like me to solve. Then like and share so that more people can have access to this great content. Till I come your way again, keep doing maths right. Bye.